Hello, everybody, wherever you may be. And it is my great pleasure to be the next cab off the rank in this 24-hour global heat flow day. I am Dr. Graeme Beardsmore. I'm at the University of Melbourne here in sunny Melbourne, Australia, where it is just turned 5 p.m. And it's a nice sunny day outside here. So, as I say, wherever you are in the world, welcome. I'm going to be talking on surface heat flow measurements for mineral exploration. It's a title. Um, it's a theme rather than any specific scientific outcomes. So I'll forge on ahead, and hopefully that'll make more sense as I get into this presentation. Key thing is here though that thermal properties can be diagnostic tools for mineral exploration, and here we have a an image of a particularly handsome fellow from about 10 years ago now on the just a visual image on the left and a thermal infrared image on the right. And for trained geophysicists like myself in the audience, you may immediately spot an anomaly in the right-hand image, which I've now circled here. It is my gold wedding band. And clearly, on that thermal image on the right-hand side, the gold stands out as a negative thermal image. This is a cartoon explanation and illustration more than anything. It's due to gold's different um, irradiance properties in infrared, but it's just really to illustrate that if we understand thermal properties and the effect of mineral systems on thermal properties, then heat flow science can be used as an exploration tool. And this is not a new idea. I found this quote from Applebaum's Applied Geothermics book from 2014 that Radionov and Sofronov, 1935, were the first to introduce near-surface thermal prospecting in the USSR, and not just introduce it, but used it successfully to locate and discover the Degtyask copper pyrite deposit. And forgive my my attempts at Russian accent there. So we're going back sort of almost 100 years there for using thermal properties, thermal measurements as mineral exploration tool. But anybody who's dabbled in mineral exploration would be aware that nothing has really progressed in the intervening 90 to 100 years. You don't immediately think heat flow and thermal measurements when you talk about exploring for mineral systems. Well, some people don't. Um, I didn't come up with this concept. As I say, it's the Russians were doing it almost 100 years ago. I myself published with one of my PhD students this article in the MESA Journal, which is a South Australian government uh, minerals geological survey publication. And 20 years ago now, I had to sort of stop and take a double take on that, but it was 20 years ago that Chris Matthews and I put this article in the MESA Journal about whether heat flow could be a uranium exploration and modeling tool. And we thought we demonstrated quite convincingly that it could. And one of the images that we drew on in that article was this one down in the bottom right, which shows a heat flow cross section across the top of two known, discovered, and mined uranium-rich copper gold deposits in the state of South Australia, in Australia. So we have the enormous Olympic Dam ore body, which produces some significant amount of the world's uranium, copper, and gold, and nearby, within about 20 kilometers, there's the Acropolis iron oxide copper gold deposit, and both of them are significantly elevated in terrestrial heat flow, uh, surface heat flow. So uh, temperature gradients, thermal conductivities have been measured in boreholes across the top of both these ore bodies and in other boreholes extending off to the sides of these ore bodies for some tens of kilometers. And those heat flow determinations have shown quite clearly that the iron oxide copper gold uranium rich deposits are significant heat generating bodies with significant heat flow signatures, surface heat flow signatures above them. So if we can collect enough surface heat flow measurements across prospective areas for these sorts of uranium-rich iron oxide copper gold deposits, then heat flow becomes quite a useful exploration tool. Now, so this data, this concept, was published another almost 20 years before Chris Matthews and my opinion piece in the MESA journal. So we're going back to 1989 when my PhD supervisor and co-supervisor, Jim Cull and Greg Hausman, published this article in Geophysics Journal back in 1989, where they did demonstrate quite convincingly that iron oxide, copper, gold, uranium deposits are significant heat generating ore bodies with signatures, heat flow signatures that can be detected at the Earth's surface, albeit in boreholes drilled into the Earth's surface, but still quite a detectable heat flow signature. And so this is at 125 milliwatts per square meter in heat flow units, above a background in that part of the world of about 75. And I've got a line drawn here at 65, but really through central South Australia. The baseline heat flow is about 75 milliwatts per square meter, but the Olympic Dam ore body in particular is about 50 milliwatts per square meter above that baseline level, so very easily detectable in heat flow determinations in boreholes. Uh, Uranium-rich iron oxide copper gold deposits are not the only subsurface phenomena that affect the temperature field in the Earth and surface heat flow. Given that most of my work is in the geothermal energy sector, obviously convecting hydrothermal cells bring heat very effectively to near surface, from which it can then conduct through to the surface and with a elevated terrestrial heat flow signature above convection cells, uranium concentrations, as I've just mentioned, cooling magma bodies in the mid to upper crust, obviously a very strong heat sources and have high thermal signatures above them. Areas of basement with elevated radioactivity within the basement, and I'm thinking from Australian context of the granodiorite that underlies the Cooper Basin in Central Australia and was the target for a lot of geothermal exploration and attempted development back 15 to 20 years ago. Salt diapirs can channel heat. Major faults can affect heat through refraction or affecting groundwater flow paths. Thermally conductive ore bodies can affect surface heat flow signatures through refraction as well. So there are any number of these sort of underground phenomenon that can impact the surface heat flow. So if we were able to employ surface heat flow measurement technique extensively across prospective areas, it could become a very valuable additional geophysical layer of information that can help target expensive drill bores. So that's sort of the premise of this talk, and something, as I said, that I've been talking and writing about for at least 20 years, and that what I myself inherited from my own PhD supervisory team 20 years before that, but it hasn't really caught on. So what would be really great if we could generate a heat flow map of the world or a heat flow map of a region or a prospective area with the same spatial resolution as we now do with gravity or magnetics or any number of other geophysical data sets. So here we have one visualization of the Earth's gravitational field. Excuse me. Which you can see is quite high resolution. You could zoom in on any part of the Earth's surface. This is a satellite-derived map, I think. We can zoom in on any part of the surface and zoom in quite close to within definitely tens of kilometers resolution, if not individual kilometers of resolution, anywhere on the Earth's surface, and start to detect local gravity anomalies, which may point to hidden ore bodies or other geological phenomenon in the subsurface. On the right-hand side, we have one visualization of the Earth's surface heat flow field. This one produced by Gurtorb et al. In 2011. So not necessarily a recent publication. So 15 years old now. There have been sort of a handful or more of other visualizations of the Earth's heat flow field, but they're all kind of constrained by the fact that that the heat flow field, or that these sorts of maps are by requirement really interpolated from fairly dispersed set of heat flow data points. So we don't have the same density of heat flow data point information that we do for the Earth's gravity field, for example, to produce the same level of resolution and detail in the Earth's heat flow map. If we could, then the Earth's heat flow map could become as diagnostic as the gravity map or the magnetics map or other geophysical type surface information maps to understand the subsurface. And so thinking at it from a mathematical perspective, there's no theoretical reason why we shouldn't be able to do that to produce a heat flow map, because the conductive heat flow is a potential field technique. So the Earth's subsurface temperature field obeys the conductive subsurface temperature field obeys potential field laws. The mathematics governing conductive heat flow is actually directly analogous to the mathematics governing gravity, magnetics, electromagnetics, and other potential field techniques. So we have the gravity representation, mathematical representation over here. I'm not going to read it out, but I'm just showing that we can write a directly analogous representation of the mathematics governing conductive heat flow, and that's over on the right-hand side. So in these equations, on the left-hand side for gravity, small g is the gravitational acceleration at the Earth's surface, which we can take a magnetometer around and measure that. And uppercase U is the gravitational potential at location or elevation R. And so if we can measure G, that tells us something about the gravitational potential in three-dimensional space. By analogy, well, go on to the next slide here. So mathematically, we can draw direct analogies between the mathematics of gravity and surface gravity measurements, and the theoretical mathematics governing conductive heat flow, and what that would mean in terms of surface measurements that we could make to build a surface heat flow map at high resolution. So the direct mathematical analogies are that gravitational potential in the gravity system maps directly to temperature. So the three-dimensional temperature field in the Earth is directly mathematically analogous to the gravitational potential at depth or elevation above the Earth. The gravitational acceleration vector G is directly analogous to the temperature gradient at the Earth's surface. So measuring gravitational acceleration with a gravitometer at the Earth's surface should theoretically and mathematically be the equivalent and provide the equivalent amount of information as measuring the temperature gradient at the Earth's surface. And taking measurements of the gravitational acceleration at the Earth's surface tells us something about the distribution of density and mass underground, whereas taking measurements of the temperature gradient at the Earth's surface should, theoretically and mathematically, give us information about the distribution of internal heat generation and the total amount of heat being generated in the Earth. And the last variable from these equations, so we have capital G on the gravity side of this slide, which is the universal gravity constant, and the direct analogy of that in conductive heat flow in the mathematics would be the thermal conductivity of the rocks. So if we just put that into simple words, a body of anomalous density in the ground that affects the gravity signature that we can map and detect at the Earth's surface is the equivalent mathematically of a body that's generating anomalous amounts of heat in the ground that we could theoretically detect by making measurements of the Earth's temperature gradient at the Earth's surface. So mathematically, there's cause to hope and think that we could produce heat flow maps at the same resolution as a gravity map and start to really understand the thermal properties of the ground from surface measurements. So on gravity, we infer the details about the distribution of bodies of anomalous mass within the Earth by making measurements of the gravitational acceleration at the Earth's surface. That's something that we do, and not just at the Earth's surface, but we have airborne gravity now, we have satellite-derived gravity maps. So we can take these measurements at different elevations, but what we get out of it is inferring details about the distribution of bodies of anomalous mass in the Earth. So if we just translate that into what that would mean in terms of the thermal field and heat flow, direct translation would be that we can infer details about the distribution of bodies generating heat at anomalous rates within the Earth from measurements of the temperature gradient at the Earth's surface. So that's what the maths tells us. So theoretically, anybody who's done geophysics in undergraduate would be familiar with these bell-shaped curves that we expect to see in the gravity field amongst on top of, above a spherical anomalous mass. We can do the same theoretical heat flow modeling, and we would see the same bell-shaped curve in surface heat flow if we have a buried source of heat. So this is a simple two-dimensional heat flow model with an anomalous source of heat within homogeneous background material, and the theory and the maths predicts this elevated bell-shaped heat flow curve above that buried heat generating body. And in practice, we can take profiles of gravity and then develop quite detailed subsurface models, which can then be used to predict the surface gravity field and start to refine our understanding of the subsurface based on the gravity. And here's this image again from so close to 40 years ago now, showing that, although this is very, very low resolution, covering sort of 60 kilometers horizontal with just 6 data points, so about 10 kilometers apart each data point. But even at this low spatial resolution, we're still seeing these surface anomalies in heat flow above the ore bodies. So it works. It works mathematically. We can model it, and evidence suggests that it actually works. These two ore bodies have detectable heat flow signatures. So why don't we do it? Um, so I'll come back to surface measurements. I just want to sort of diverge slightly for a moment and point out there's the sort of low-hanging fruit in the heat flow work. Uh, every mineral exploration company drills boreholes. They might identify targets based on gravity and magnetics and potential field and their understanding of the subsurface geology built up from multiple layers of geoscientific evidence. And then they'll drill a borehole. Now, not every borehole hits the ore body. So here's this mysterious buried ore body that showed up on a gravity map and or a magnetics map, and somehow this inclined drill rig managed to drill a vertical bore, which found nothing. It was barren. So they took samples, brought them to the surface, and just found country rock. So I thought, well, maybe we missed the ore body. Maybe we have to drill another expensive borehole somewhere else. We'll go back and reanalyze the geophysics. Um, but perhaps information can be gained from this near miss. So if we sort of zoom in on this square, the borehole down the middle, and let's say this ore body that was being explored for is one of those uranium-rich iron oxide copper gold deposits. And just as an aside, there's been sort of statistical estimates that there may be as many as 10 uh, Olympic Dam size uranium-rich iron oxide copper gold deposits still to discover in South Australia. And the challenge is there are some 5,000 individual gravity anomalies, any one of which, or any 10 of which, could be these monster ore deposits, and they're deeply buried. They're like under 600 or 700 meters of cover. So the drill holes you can't just effectively, efficiently, cheaply go around and drill every one of these 5,000 uh, anomalies because they're very expensive to drill. So what if a temperature log was taken in each barren drill hole? Could that temperature log tell us something about whether we were close to a uh, a heat source, an ore body generating anomalous amounts of heat? So on this chart down here, there's a temperature scale across the top there. So this is just the hypothetical temperature log, the white line that we might expect to see if if this particular anomalous body was not generating any heat. If A, the internal heat generation is zero, then this is sort of the background temperature log that we might expect to see. If this body is generating a lot of heat, like a lot more than 0 microwatts per cubic meter, and the Olympic Dam ore bodies in the tens of microwatts per cubic meter, I think, on average, then we would expect to see an elevated geotherm. But the degree of elevation's not that great. It's like maybe 1 degree difference at the bottom of this arbitrary depth of bore. And even if you did measure that, um, it's not immediately obvious whether that's an anomalous gradient or whether that's the background gradient. So you need something to compare it against to know if it's higher than expected or not. But if we, instead of just measuring the temperature log like that, what if we also took lots of thermal conductivity samples from the core that's almost always collected from these boreholes, measured the thermal conductivity, and turned these temperature logs into heat flow profiles? Then then we expect to see that the modeling tells us that we would expect to find a different story, and for a barren anomaly, not generating any heat, we might expect to see this sort of heat flow profile, so gradual increase due to channeling of heat, so refraction of heat up what could be an iron-rich but not economically viable body of rock buried, and a lot of those barren 5,000 gravity anomalies are just sort of accumulation of iron and with no commercial value. So iron-rich bodies of rock will probably channel heat conductively and may well affect the flow of heat and what that's doing to the vertical heat flow signature in the close proximity. But if it's generating heat, then as the bore goes past the top and starts sort of going down beside this heat generating body, the detected heat flow actually drops off quite dramatically. And once if the borehole was to pass directly beyond the lower extent of the ore body, then the heat flow would probably level out, but at a much lower level than what it's seen at the surface. So even uh, taking detailed heat flow measurements in a barren borehole could yield very valuable information about whether there's a large accumulation of heat generating material nearby. And that is likely to give a lot more value, provide a lot of value, in fact. You could do the same thing with gravity, for example, and you would probably just very likely see this red type line, regardless of whether it was an economic ore body or not, because a lot of these holes they are drilled based on gravity anyway. So there's by definition already known that there's a density anomaly. But what's not known is whether or not these are high heat producing bodies. And if it's a high heat producing body, almost certainly it's going to be an economically viable ore body. So I've sort of given this story. We made this pitch 20 years ago in the Mesa Journal. I've given a very similar talk at conferences and even one-on-one to companies. And just I just don't get buy-in, and I don't understand it. I honestly don't. The incidental incremental cost of doing a temperature log and thermal conductivity measurements is trivial compared to the cost of the bore. But companies, they're just not buying into the concept, and I really don't understand it. But the key point is that a heat flow log in a barren borehole can, in principle, detect a near miss, but you'd have to do very careful heat flow work. But the tools are available, and the science is robust. So I'm just sort of spreading the word to anybody who'll listen, and I'm sure that one day some brave mining company, exploration company executive will decide to do this work and just see what happens. But out of the borehole and back to the surface, what about detecting buried heat sources from surface measurements? So, so the holy grail, if you like, is to produce a heat flow map of the world or a heat flow map of prospective mineral exploration regions at the same resolution and knowledge value as we currently do with gravity. And gravity is the only example, but gravity here uh, just represents a whole lot of other geophysical surveys which are done, gravity, magnetics, MT, other sorts of electrical methods. Passive seismic is a growing field these days. Wouldn't it be great if we could produce the same high resolution maps for heat and heat flow? So with gravity, we just take a gravity meter like like this one, and you just move it across the Earth's surface, maybe every 20 meters. Take a quick gravity measurement, and you can build up very detailed surface gravity maps because we have this very mobile, very portable, very accurate, very reliable, and very available surface uh, data collection tool. What do we have for collecting heat? Nothing at the moment. And why is that? Because even though mathematically they're very similar, conductive heat flow and gravity, from a practical application point of view, there are three major challenges for making surface heat flow maps as effective and efficient as making gravity maps. The first challenge is that This variable on the gravity side of the equation, the right-hand side of the gravity equation, 4 pi g, is a constant. Wherever you go in the universe, 4 pi g is 4 pi g. It doesn't change. It doesn't change anywhere on the Earth's surface. It doesn't change if you go to the moon and do this. It doesn't change if you're in an underground mine. 4 pi g is 4 pi g wherever you go. It's a constant. The equivalent variable for the heat flow equation is -1 over thermal conductivity. So the direct mathematical equivalent for heat flow, for conductive heat flow, is -1 over thermal conductivity. Thermal conductivity is not a constant. Thermal conductivity is variable. It's variable on almost any length scale you bear to look. You bear to look. We have Yuri Popov talking later in this 24 hours. He's demonstrated in immense detail that thermal conductivity varies at millimeter scale. I'm sure if we look down even closer, it would vary at atomic scale. So almost any scale that you look at, thermal conductivity varies. So -1 on thermal conductivity varies. We can't just eliminate this part of the equation and expect that it's constant. Make measurements and generate maps because this varies. So the implication is that the subsurface temperature field varies as a function of both the anomalous underground heat generating body and the thermal conductivity of the rocks. So the consequence is that we can't just measure temperature gradient, even though that's the analogy of measuring gravitational acceleration, is to measure temperature gradient, but we can't just rely on measuring temperature gradient at the Earth's surface and think we're going to get the same sort of information value as we do with gravity. We have to measure, at the very minimum, both temperature gradient and the thermal conductivity to get the same level of information as a single gravitational acceleration measurement. So that's the first challenge and the consequence of that challenge. So we need at least two different sensors for our surface instruments, something to measure temperature, so a thermometer, and something to measure thermal conductivity. So probably not a divided bar, but some sort of sensor to tell us the thermal conductivity. So on to the second challenge. So gravity, as everybody from Newton onwards has approximated at least, is uniform throughout space. These gravitons in talkie marks. If you think of a particle that carries gravitational information between different masses, gravitons travel uniformly through all points in space and time. They have a single mode of transfer between masses. So without getting into Einstein's equations and things, to all intents and purposes, if you have two different masses anywhere in the universe, they'll be having the same gravitational impact on each other as any other two masses anywhere in the universe. So, and it's instantaneous. You instantaneously move one mass, the effect on the other mass is instantaneous. So that's gravity. So very simple physical foundation to build gravity maps on. On heat flow, however, conductive heat flow, sure, conduction is very simple, the math is very simple, but it's only one mode of heat transfer. There are two other major modes of heat transfer, advection and radiation. Or not even major modes, they are the other two modes of heat transfer, advection or radiation. And advection and radiation absolutely dominate once you reach the Earth's surface, and any heat coming out of the Earth gets into the atmosphere, and suddenly conduction is irrelevant, and it's all about advection and radiation as transferring thermal energy into the atmosphere. So the consequence of that, if we want to build a heat flow map of the Earth's surface, is that we have to measure the heat flow before it reaches the atmosphere. So we can't simply have an instrument that we plonk down on the Earth's surface like a gravity meter. we actually have to put our instruments into the surface so that the advective effect, advection or convection, or radiation reduced down to sort of insignificant levels compared to conduction. So not only do we need a thermometer and some sort of sensor for thermal conductivity, but we have to put both those sensors actually into the ground rather than just put them on the Earth's surface. So that's the second challenge. The third and arguably the biggest challenge is that this big burning ball of hydrogen and well, mainly hydrogen circles around the Earth at least once a day in my Earth-centric universe, and then annually it also sort of moves further away and gets closer to each point on the Earth's surface. That affects gravity measurements. It also affects thermal measurements. So gravity, yes, as this big ball of mass moves around the Earth, and also as this smaller rocky ball moves around the Earth, the moon, it causes an impact on the observed gravity field at the Earth's surface. Um, and we can predict that because we know the mass of the sun, we know the mass of the moon, we know their cycles that they revolve around the Earth, and we know the mathematics controlling gravitational attraction, and so we can work out and calculate quite precisely what the impact on the Earth's surface gravity signature is going to be from those cycles. It is predictable, and not only is it predictable, it also turns out to be relatively small compared to the size of the gravity anomalies that we tend to look for in mineral exploration. So only about 10% of the expected size of an ore body gravity anomaly is observed in the highly predictable gravity effect of the sun rotating around the Earth each day and the moon each month. Over on the thermal side, though, that daily radiation from the sun bearing down on the Earth's surface, heating the shallow soil, that heat sort of conducts into the ground during the day. At night, the sun disappears, and the warmed Earth starts to conduct and then radiate that heat back out into space again. And that obviously on a daily cycle and also at longer period on an annual cycle affects the temperature gradient in the shallow subsurface and hence the heat flow that we're trying to map, and not by a small amount either. So the effect of the sun on the gravity signal is about 10% of the size of an anomaly we're trying to detect. The effect of the sun on a thermal signal is arguably about 1,000 times the size of the anomaly that we might expect to observe or hope to observe, pray to observe above a buried heat-producing ore body. And to make matters far, far worse, it's not even predictable. It's chaotic. So the impact of the sun is not only huge compared to what we're trying to detect, that subtle subsurface heat flow signal or level of heat flow. It's also chaotic. We can't predict a day or two in advance what the effect of the sun on the shallow temperature gradient is going to be at the resolution and precision that we would need to map heat flow. So there are strategies to address that. And the chief strategy would be to collect long time series of data and do some sophisticated filtering to remove that daily thermal signal imposed by the sun. So they are the three challenges which can be basically wrapped up into we need to put precise temperature and thermal conductivity sensors into the ground and record for long periods of time, and then do sophisticated signal analysis to hope to then extract the quite subtle subsurface heat flow signature, heat flow value. So we put all those together, and if we can come up with an instrument to do that, then there is a glimmer of hope that we could potentially start to produce this sort of resolution heat flow map. So here's the aspiration. So we produce gravity maps now by taking transits and collecting gravity data on regular grids or across cross sections profiles. We collect magnetic data almost regularly from airborne instruments and produce magnetics maps. And these two images are lifted from an article about the discovery using geophysics of the Khamsin iron oxide copper gold deposit on the Gawler Craton in South Australia. So exactly one of these ore deposit types that I was showing, probably also heat generating bodies. So there was a bit of luck. Yes, it was a gravity anomaly, this particular ore body. Yes, there was a magnetic anomaly, and a brave company drilled it, and they did make a discovery. But for every one of these gravity anomalies, in particular, only a small percentage of them are going to end up being mineral discoveries. But if we could put a third overlying set of data that produced an equivalent looking map for heat flow, if we had coexisting gravity, magnetics, and heat flow anomalies, that would massively increase the chance that it is actually a uranium-bearing iron oxide copper gold deposit. So, what sort of accuracy would we require? So normal heat flow on continental areas of the world, and Australia being no exception, is about 65 milliwatts per square meter. Anomalous heat flow above a heat producing ore body of potentially economic value might be anything above about 80 milliwatts per square meter that we would expect, and that modeling would predict as the heat flow above an anomalous heat producing body. The thermal conductivity in the shallow, in the top meter or two of the ground, from experience, averages about 1 to 1.5 watts per meter Kelvin in areas that I've made these sorts of measurements. So what sort of temperature gradient anomaly would we expect? So we just take the heat flow anomaly, divide by the thermal conductivity, and we find that the normal shallow temperature gradient, undisturbed by the sun going overhead each day, would be about 0.043 degrees Celsius per meter. An anomalous gradient might be about 1/100th of a degree per meter above that. So we would need an instrument able to detect anomalous temperature at 1 meter depth of about 1/100th of a degree. Knowing that the sun is massively affecting the temperature at 1 meter depth by up to about 10 degrees Celsius every year. So heats up in summer, cools down in winter, and that drift is on the order of about 10 degrees Celsius on a year-to-year basis, and we would need to detect a temperature anomaly on the order of about 1/100th of a degree, so about 3 orders of magnitude noise to signal ratio. So noise, being the sun going overhead on an annual basis, is about 1,000 times the scale of the anomaly. Doesn't scare me. That's similar scales of signal to noise have been solved for other potential fields, and airborne gravity is one of those prime examples. So here's an instrument that I and a very long growing list of collaborators have been developing, going back probably started on this 15-20 years ago now, and it's on its third or fourth iteration now, and we call it the heat needle, for want of a better term, and it is intended to be a tool to precisely, accurately, and cost effectively map conductive heat flow at the Earth's surface. So to solve all those three challenges that I laid out, and it's about 1 meter tall. Is a standard Mexican for scale, It's standard Mexican's about 1.5 meters. So this tool, it's about 1.2 meters, and this little Coke bottle size head sits on top. So we hammer these things into the ground. We slip these very sensitive temperature sensors down the inside of this stainless steel tube once it's been hammered into the ground, and we attach some aluminium shielding to protect it from direct uh, sunlight, and then we just leave them. We leave them to passively collect temperature, long time series of temperature measurements, and long in different experiments have stretched from about 8 weeks through to just coming up to 2 years for the longest deployment. We've got three of these in the ground in South Australia at the moment. They've been there now continuously for 2 years, and they're just passively, largely collecting very precise, accurate temperature information at 7 different depths, from the surface down to 1.1 meters depth. So it's really just the top meter that we are sensing, and and the temperature data do follow these very uh, the predicted relationship that as we go deeper into the ground, we see the temperature decaying in amplitude and a phase shift uh, as well. So very steep temperature variations at the surface, decay in both amplitude and the time of the peaks shifts in a manner that's directly correlatable with the thermal diffusivity of the ground. So also in these heat needles is an active heating element that periodically we can hook up battery power and a little control box, and do a heat needle type thermal conductivity measurement of the soil as well, and we get thermal conductivity at 5 different depths. The surface sensor is doesn't really give an accurate thermal conductivity, but we effectively get a thermal conductivity at 10 centimeters depth, 30 centimeters, 50 centimeters, 70 centimeters, and I hope shortly to be able to infer the thermal conductivity at 1.1 meters depth too, although it doesn't, the way the system's built, it doesn't accurately conform to the infinite line source model. So I have to do some more sophisticated type of numerical modeling for that. But when we revisit these sites and periodically take those thermal conductivity measurements, they start to build up a very believable thermal conductivity profile history. And the sites that we've now been collecting for 2 years, we do see a very nice seasonally variable heat thermal conductivity pattern at the different depths. So I'm satisfied that the instrument is accurately collecting very precise temperatures and thermal conductivities, and hence heat flow, and it's doing it at 15-minute intervals on the temperatures, and we try to get out to these sites once every couple of months to do the thermal conductivities. So I'm going to wrap up because it's almost used up my full hour. Thank you for listening. Um, so we're getting close. I'd say we're not quite there yet, but I'm actually happy that these instruments are collecting the high fidelity data that's required, and really the next step is the sophisticated signal processing that is still required to tease out that subtle signal from the very overpowering noise of the solar radiation. So I'll say we're not quite there yet, but we are getting closer. I think it is a tractable problem, and I sort of know the steps that need to be taken. And I've got a very talented PhD student at the moment visiting from China who's doing some of the data uh, analysis that I've been wanting to do for about 10 years, and now finally Xingwei is helping me and making very exciting progress. So I'll say we're not quite there yet, but we are getting closer to the point where we may start to hint about thinking about maybe one day getting this sort of high precision surface heat flow using a relatively easy to install almost surface instrument. And the Geological Survey of Western Australia has just commissioned 18 of these, and they're going to be placing them out uh, in by far the biggest trial yet across Western Australia in the second half of this year. So we're about to be overwhelmed with new data to help build this tool. So that's the end of my slides. So I've left less than 10 minutes for discussion and questions, but happy to take them.